Hello viewers, my name is Samuel D. Kwede, and I'm your tutor for physics today, and we're going to continue our discussion today on black body radiation, quantized energy, and the photoelectric effect. But because of time, we're going to take the first one, and if time permits, we proceed to the other. But if we do not finish, you have to watch out for the next lesson. It's a continuation of what we're going to do. So now let's start from the first. Now, at the start of the 20th century, our understanding of the physical world was changing rapidly, of course. If you can recall my previous lessons, I was able to explain the discovery of the electron, and also I was able to tell you about the cathode ray experiment, the famous one that led to the discovery of the electron. And so at the start of this 20th century, our understanding of the physical world was changing rapidly. The electron was discovered. There was evidence that the atom, which had been considered as the smallest particle from Dartin's idea, all matter made up of atoms, which are indivisible. Remember that concept from Dartin, and we had an internal structure of the atom. We were able to discuss the internal structure of the atoms. We now debunk that theorem that the ultimate end of matter was atom, and we ended up discovering the other component of the atom. So, and from our previous lessons also, we were able to look at the cathode ray and the cathode ray experiment done by JJ. We were able to discover the electrons. So now, the end of that century, our target was actually how to challenge ourselves on light. Light was a big challenge. What is this light? And what is the constituent of that light? So our topic first here is to tell us what bodies look like. So what is a black body? It's a body which absorbs all electromagnetic radiation as light. I just told you that the challenge in the 19th century, after discovery, all of that was to see what is the component of this light. So if light falling on bodies, some bodies will absorb all the radiation, the electromagnetic radiation, that's the light that falls on it. And when that body absorbs all the electromagnetic radiation falling on it, we call it a black body. So when a radiation falls on a body, part of this radiation will be reflected and part will be absorbed, and the rest will be transmitted. Now, the fraction of transmission or absorbing or even reflecting is given by that equation there. Remember I said part of it, when light falls on a body, part of that light is reflected, part is absorbed, and part is transmitted. So all those fractions added together will always give us 1. So if I have an object that can reflect all the light and absorb nothing and transmit nothing as well, that object becomes a white body. And conversely, if I have an object that will not reflect but absorb all the radiation falling on it and transmit nothing, now that object becomes a black body. That's what we're talking about here. A black body is an object that absorbs all the radiation that falls on it. So now we look at the absorption fraction and the reflection fraction, and even the transmission fractions. There are some other objects that allow the light to transmit through them, like glass prisms and stuff like that. So now let's look at an example of this black body. You could take it from the fact that it could be lamp black. Some of you have come across lamp black, or platinum black. It's a black body. It absorbs all the radiation falling on it. Now, all objects emits electromagnetic radiation, which depends on their temperature. That is the thermal radiation, you know. A black body absorbs all the radiation, I just told you that. That is light, which falls on it. And because no light is reflected or transmitted, that body appears black when it is cooled. So because for the fact that it doesn't reflect or transmit, it's going to absorb all the light falling on it, then it appears black when it cools down. But however, when it is heated very well, they will always give a spectrum. And that emitted spectrum is dependent upon the temperature of that black body. That emitted spectrum is what we call the black body radiation. So for as much as it's going to be absorbing all the radiation, but it's going, when it is heated, very hot, it still emits a spectrum of radiation, which is categorized according to the temperature of the body. So it is temperature dependent. Watch out for that. We'll come back to the objective question. Now we look at this. We say, what is a normal body? Now, I just told you that it's a body, a black body is a body that absorbs all the radiation falling on it. Now, at normal room temperature, we are not aware of this radiation. So you must be also conversant with the fact that maybe you are even giving out a radiation because of the temperature. You are at normal temperature, say room temperature, you are not aware of that radiation. But all bodies give out radiation, your calculator, even the human beings, your TV, whatever. So now, but as object becomes hotter, watch out what they do. We can feel the infrared radiation. That's what you feel when you take electric iron and you fix it onto the wall and you plug in your current and it becomes heated. Now, if you bring your arm closer to it, you feel the radiation, even when the iron is not close to your body. When you go put it closer to your body, you feel the radiation. That is infrared radiation and it's heat. Now, at even hotter temperature, when the object becomes hotter as well, it glows. And when it glows, you can see that it appears red sometimes. And at a very hot temperature, a still hotter temperature, it will glow again and give other colors. So you can see the light bulb over there. When it is heated at some temperature, you saw that it became red. So the other light bulb is white. So you can continue heating the body. It will glow from red. It can go through orange, go to yellow and blue. And when it is extremely hot, it can even go up to white. And that is the stage, I think, where we have our sun. Our sun is glowing white, what we call it white light. You know, when all the radiations are visible in that. So watch out for this theorem. But before I go to that theorem, I want you to first of all remember that the body will glow as I'm increasing the temperature. It will glow from red, it goes through orange, goes through yellow, and when it is severely hot, it goes up to white, it glows white. Now, let's see how somebody tried to relate that, because the sun is at a very high temperature. So for as much as we said at that temperature, as it's glowing, it is going to change its color and becomes white. That is the idea behind the white light. Now, somebody, Wilhelm Wien, tried to discover a law that will interpret that relationship. So what he did was that he wanted to compare the wavelength of that white body and the temperature of the white body. Remember, I told you that when it is heated to some temperature, they will give out a spectrum, and that wavelength of that spectrum has a business with the temperature. So he wanted to know that. He says that the maximum wavelength associated with a black body is inversely proportional to the absolute temperature. It's inversely proportional to the absolute temperature. So what do I mean by that? So let me just emphasize that on the board. It means that the maximum wavelength associated to a black body is inversely proportional to the absolute temperature. And the absolute temperature in Kelvin, for that matter. So now, if we now see an object that is hotter, so as you're getting hotter, that's how your wavelength becomes, smaller because of inverse proportionality. So let's consider the sun. The sun has set up to a temperature of 6,000 degrees Celsius. So the sun is very hot. So what we expect from the sun, that the wavelength is going to be a shorter wavelength. So the sun gives us short wavelengths, and that short wavelength is inversely proportional to the temperature of the sun. So it is based upon this theorem that we can remove the proportionality sign, introduce a constant. Let's call that constant K, call it there. So K is equals to lambda that. So watch out for this equation. We're going to use it a lot. So now, and this constant was given by according to that gentleman, Wien, he said 898 times 10 raised to the power minus 3 meter Kelvin. Meter for wavelength and temperature for Kelvin. So that constant of proportionality was given by Mr. Wien. That's you watch out for this constant. We're going to use it a lot here. So now, how does this apply to the sun's behavior with the Earth? Remember I said that it's the maximum wavelength associated with a black body is inversely proportional to the absolute temperature. So now, if we can see an application in the greenhouse effect in cold regions, we have houses that are constructed in the cool region, where it's difficult to get sun to photosynthesize. So they depend on the greenhouse. Let's say that's the greenhouse. And this greenhouse is made up of glass, and it is actually used to preserve plants and sometimes grow plants in there even. So let's say that's a plant inside that house. You know, it's a glass house. So now that is sun which is hot at that temperature, very high temperature. Now let's say that's 6,000 degrees Celsius. Now that sun rays hits this house, and the glass of that house, it's a glass house. So that's what we call it a greenhouse effect. So I'm coming to explain that very soon. So now that sun's energy is transmitted through that glass. And when it's transmitted through the glass, it is, because this is having a high temperature, so it's coming with a short wavelength. So there is short, the wavelength is short. In that case, the short wavelength. So the radiation coming, because of the interaction here, we say high temperature is shorter wavelength. So that short wavelength will penetrate the glass, and it goes onto that earth, which is the plant in there, the plant on the soil or whatever. It gives it to that plant, and that plant use that energy to photosynthesize, and even used to preserve some of the vegetables in those countries, those cold countries. So now when these plants interact, that's the earth, the energy, its temperature is going to be it's going to emit radiation which is colder than the energy that came there. So a colder, that is a smaller temperature. Now because it's emitting, after the interaction with the radiation, the earth emits that radiation which is of colder temperature, and because the temperature is cold, you expect a longer wavelength. So now have a long wavelength. Now this long wavelength radiation, it's not going to pass through. The short wavelength will pass through the glass, but the long wavelength will not pass through the glass house. So what will happen? It will be stuck inside that glass house, and it will be circulating inside that greenhouse, and the plants will use it to photosynthesize and even preserve that plant. So that's how cold countries grow their plants. That effect is what is called the greenhouse effect. Now, we can relate this greenhouse effect to the global warming. Watch what happens there. So if this was the greenhouse, this was the greenhouse there, which is a glass house. Now, let's call it the glass house. Now, if it was the glass house, and that's, if we compare that to our situation on Earth right now, we find out that the Earth, let's say that's the Earth, let's see the sun over there, and this is our Earth. Now, the Earth is surrounded by the atmosphere, of course. Now, what happens there is that in this case, the Earth now takes the place of the plants. So now, and the sun is still there, it's still hot. Now bringing a very massive temperature there. So that radiation from the sun will pass through the atmosphere, and because it is short wavelength, it passes through the atmosphere and now enters the earth. And now the earth will use it, and the earth serves as the plant. And when the earth serves as this plant, then there is going to be a particular catastrophe that is happening now. That is the more reason why they tell you to control the rate at which you emit the carbon dioxide into the atmosphere. Because when the carbon dioxide is emitted from our industrial activities, the industrial activities of the earth will emit the carbon dioxide, and that carbon dioxide will encompass the earth and envelope the earth. And when it envelopes the earth, it's not going to serve as the glass. So that carbon dioxide serves as that glass. And when the short wavelength radiation from the penetrate through the atmosphere goes to the earth interacts with it. Now, the radiation given out by the earth is not going to pass through because it's going to be having a long wavelength in that case. Here it was a shorter wavelength. Now, this short wavelength will penetrate the atmosphere, but the one given by the earth is going to have longer wavelength, and it could not pass through the carbon dioxide, because the carbon dioxide is going to serve as the glass, and it is going to resist, and that energy will come back to the earth, because the carbon dioxide layer will block that radiation from going to outer space. So what will happen? We will have that energy returning back to the earth, and what the consequences there is that the earth becomes warmer, and when the earth becomes warmer, that is what we refer to as global warming, because the earth is the globe. And that global warming is what leads to the ice. The ice melts, you know what happens. We see that the volume of the sea will increase, and you have all these coastal cities will be trying to relocate, because you are going to, the water will claim the land. So that's what happens there. So we have seen the consequences of all of these Wien's theorem and 2, greenhouse effect, and also the global warming. So that is for global warming for you. So now we have just given you the equation there. So Wilhelm Wien's, through experimental observation, determined the following equation that's related to the color of the light and its temperature. I just established that for you. So that is the constant there I was just talking about, you see there. And this gentleman did a very good work for us. And we can use this to now answer. Watch out before you get to the questions. I said that the maximum wavelength associated with a black body radiation is inversely proportional to the temperature of that body. So you must be able to understand the link between them. So it's being the hotter the body, then the smaller the wavelength, or the shorter the wavelength, and vice versa. So now watch out from what I've said from the summary there. You say, let's look at the question. It says, what are the properties of a black body radiator? Remember, I just said that a black body radiator, a black body absorbs all the radiation that falls on it, and it doesn't re-emit anyone again. It just absorbs all. So the options read: A, it absorbs all the incident radiation and then re-emit it at a different frequency. That's not correct, because we said the black bodies don't re-emit. Now B says it is always black, even when heated to high temperature. That was wrong. I said when it's heated, it will glow to different colors, ranging from red up to even white. So C, it absorbs all the incident radiation and does not re-emit any radiation. That's what I said. I said black bodies absorb all the radiation that falls on them and do not re-emit or do not reflect or transmit. None, they absorb all of them. That is C. C is the correct answer in that question. So we have our correct answer as C. It absorbs all the incident radiation and does not re-emit any radiation. So watch out. Now the next question says, which of the following colors indicates the hottest temperature of an object? Remember, I said that it will, when the black body is heated, they are going to range from red, it will pass through red, orange, yellow, blue, and then white. When it is extremely hot, as it is becoming hotter, when it's hotter, it goes in that order there. So watch out for that question. We said, which of the following colors indicates the hottest temperature of an object? A says black, B says red, C says yellow, D says blue. So E says you need help. No, okay, we want to help you out here. So the correct answer there is, we're looking at our range here. We say the colors increases as I move from red, orange to yellow, yellow to blue, and when it's extremely hot, it goes to white. So now we have D as the correct answer, that is blue. Blue is the one at the extreme over there. So blue is correct, D is the correct answer. So we go back to the next question. Which of the following colors indicates the coolest temperature of an object? So remember, I said that they will glow, and the temperature increase, it will glow from red, and it will go in that order. Now see that red came before orange, orange is there, yellow is there, blue is there, but in this order, red came before the orange. So if you look at it, it's going to be the coolest. When it is colder, this is colder than this one. So red is the correct answer there. Which of the following colors indicates the coolest temperature of an object? It's red. A is the correct answer. B says orange, C yellow, D blue, but A is the correct answer, which is red. Watch out. Now we look at this. Now, using the Wien's displacement law, I just established that relationship for you here, so I can clean here. So see how you go through it. Now we have already established the relationship between the two, so we can now use it to do some free response question. Now watch here. We have, can just clean, so you can see properly. Now remember the relationship according to Wien says the wavelength is inversely proportional to that. So you now have wavelength as K over T, remember that. So K is wavelength, that. And now that constant of proportionality I have just given you in this question is not given, but that is already perceived here. So we know that constant as 2.898 times 10 raised to the power minus 3, and is equals to, now this guy says, what is the wavelength that is associated with that maximum? So I read the question. Using Wien's displacement law, what wavelength is the maximum contributor to the object's color at the temperature of 4000 Kelvin? So now we want to find that wavelength. So we know the temperature is 4,000 kelvins. So I can divide that, and we have 4,000. So this guy, so what is this temperature? After dividing both sides by 4,000 cancels that. So we have 2.898 times 10 to raise to the power minus 3 divided by 4,000 gives you that wavelength. So if you punch that on your calculator, you have something like 724 nanometer. That is times 10 raised to the power minus 9 meter. Or you have 724 nanometer. So if you look at the options, you have A says 314 nanometer A. Now B says 450 nanometer. C is 592 nanometer. D 724 nanometer. And now we can now settle down on D. D is 724 nanometer, if you can punch that from your calculator. So the correct option there is D, 724 nanometer. Right, so we look at the black body as the temperature. The figure shows black body radiation cause of a black body at 3 different temperatures, and the classical physics prediction of the intensity of the light at 5,000 Kelvin. So watch this one. That was another discrepancy here. That was a clash between classical physics and quantum physics. You know, classical physics deals with Newtonian physics, where the laws of Newton holds, and quantum physics needed to match the two together. But as this experiment brought a big problem between the classical physics and the quantum world, or what happens with when you theorize, meaning you give a theory and you predict a theory and you now hypothesize that prediction, then you now discover, or you do the experiment yourself and you discover different data. What will happen? That's how do you relate your theory you have asserted and what you have seen naturally, but what you have seen in real sense. So this was one of the problems. You know, it was perceived under the classical theorem, as you can see the 5,000 K, the black line there tells you that the wavelength of this black body at different temperatures, you know, as you move, I can just draw that for you. Here you have, here, so you see, here, you see the other colors, so right here, that is 5,000, K, 4,000, let's see, and you have 3,000, that other. Now this is somewhere, let's say 0.5, so this is around 0.5, 1, 1.5, as you can see over there. 2, this is the wavelengths in meters. Now see that spectral zones you see here. We can see that I have the ultraviolet somewhere here, and around here I have visible light. This is the spectrum, and you have the infrared. Now see that it's a line. Let me give another color to that line so you see the difference. So the blue line somewhere there, you see what classical physics was talking about here. This is a classical prediction. It's a classical physics predicted that when the wavelength of the lines, remember I'm moving this way, I'm reducing the wavelength. When I'm reducing the wavelength and the intensity, this was the intensity. The intensity, let's say it's 2, 4, 6, 8 in that order. Now I have that. So as I was increasing, if I'm reducing the wavelength of particular radiation, black body radiation, if it's reducing, now, according to the classical prediction, that if you reduce the wavelength coming towards 0, if you are approaching 0 here, what will happen? The intensity will go to infinity. You see the asymptote over there, it's telling you that this intensity will continue to infinity. Now, it will not curve like this. So now this was what was observed. They found out that the different colors, as the wavelength, as the temperature was increasing at 3,000 Kelvin, red light in that visible spectrum was available, and they saw 4,000 as the temperature was increasing, green came, and you have you remember the spectrum of the white light? You see how they were coming there. You see red followed by green, and you see blue followed later on there. At 5,000, the highest peak there is 5,000, and that's the blue. So if you see the visible region there, that's temperature 5,000, the visible region of the spectrum gave light of different colors. You see that color? You see red, you have orange, you have blue, and you have even the highest they are blue. But the classical model just did not predict that. It says that as I reduced the wavelengths going towards 0, the classical model here now gives that black line. That black line tells you that the intensity becomes infinite. See, it's cut there. You see the asymptote. It's infinite. The intensity becomes infinite, which was what was predicted. But what was observed after the experimental data was a different thing. This was what they discovered. They saw the red here, and they saw the green and blues here. This was what was observed, and that this gave a difference between the asserted or purported theorem or purported discovery and what they have already seen experimentally. So that's needed to be corrected somehow. So when you plot the two, you see you have the x-axis plotting the wavelength and the wavelength emitted by the dark body, and the y-axis showing how intensified is that wavelength. That is, how intensified is the light. That is the intensity on the y-axis. So you see the pattern of the curves, which is a deviant from what classical theorem predicted, as you see with the black line over there. So the same goes. You see the red and blue green colors. They saw the actual data when they did the experiment. Now, based upon their prediction, what they have seen now from doing the experiment was different from the prediction. The classical model now predicted that as you reduce the wavelength, moving from higher wavelengths, running down towards zero, the intensity of the light becomes infinite, and that was not what they observed. So there was a discrepancy there. So see what happened later on. The black line is what the existing physics theorem predicted what would happen when the temperature of the object will reach 5,000. That was what they were predicting, that when the temperature of the object reach 5,000, this is what happens. You will see the black line, the intensity goes to infinity. So now, well, that was not what they saw. Now the light with the most intensity shifted from the longer wavelengths. That's what I'm saying. Here is the longer wavelength here. So if I'm supposed to magnify them, you see that the magnitude of the wavelength. So as I'm coming down this way, I'm reducing the wavelength. So the higher intensified light, which is around here, the wavelength was shifting down towards the visible spectrum. That is towards the visible spectrum, like I said over there. And it starts as red light. It begins to glow as red light, like what I said. And it goes through yellow, go to blue, and finally at 5,000 Kelvin, all the colors of the spectrum are present. And when all the colors are visible, that object becomes a white light. That's what we call the white light, which is the sun. The sun is in that category right now. So now see how this gave us. But we can now see a real problem that arises from this. The classical theory predicted, that is the black line, and the measured data, which is the blue and the green and the red, they predicted different ones. So you see the lines of the black and the lines of the colors, they are different. So the hint is that the black line just keeps increasing as the wavelength approaches zero. That's what the classical model, classical physics purported, but that's not what we saw. So let's see what was the conclusion. The classical theory shows that the intensity of the emitted radiation approaches infinity as the wavelength gets shorter, which is not what happened. Shorter wavelength means that the light is moving into the ultraviolet end of the spectrum. So now we can take some questions here. Yeah, see one. How does using a graph of observed data from a black body radiation versus the theoretical prediction of the data helps illuminate problems with the theorem? The answer there is that if the experiment or observation is properly done, then the theory must produce results that match the data. If not, the theory must be modified, or if not possible, a new theory must be created. The graph clearly shows a major discrepancies between the black body observed and its theoretical predicted behavior at 5,000 Kelvin. So question number 2, as the temperature of the black body increases, what happens to the color of the emitted light? I told you that as it increases, it moves. A says it goes from white to black, wrong answer. B, it moves from red to yellow and to white. And C says it moves from white to red to yellow. D says it moves from visible light to infrared. B is the correct answer because I told you that it moves from red, go through orange to yellow and to white. So we'll have B as the correct answer. It moves from red to yellow to white. So the next question is, what is the problem with the theoretical prediction of the black body behavior as its temperature increases? The problem here, A says the theory predicts that the intensity of the emitted light does not change as the wavelength decreases. Now, B says the theory predicts that the intensity of the emitted light approaches zero as the wavelength increases. C says the theory predicts that the intensity of the emitted light approaches zero as the wavelength decreases. And D says the theory predicts that the intensity of the emitted light becomes infinite as the wavelength decreases. And that's what I said. So the correct answer there is D. The theory predicts that the intensity of the emitted light becomes infinite as the wavelength decreases. Now, you have some free response here. We have to calculate that energy before the time goes. We said calculate the temperature of that black body. So this, I can just go through that quickly there. Calculate the temperature. So now we already know the link between, we have temperature there. So I can calculate the temperature by K over lambda. So the temperature is going to be, the constant is given 2.898 times 10 raised to the power minus 3 divided by the wavelength is given there as 20 times 10 raised to the power minus 9. Remember the nanometer. So the temperature is given there as, if you use your calculator, you have times 10 raised to the power minus 10 raised to the power 5 Kelvin. So you must be able to do that. That is the free response. We've done that. So now we have the Planck's quantum hypothesis. Because of the tremendous discrepancies, somebody needed to correct the error. The error was through the prediction of Mr. Planck. Planck predicted that the energy of that light is directly proportional to its frequency. That's where the equation came from. The energy of that light was, that's just a prediction that worked. He didn't have any justification for that, but it just worked because of what he predicted. He says the quantum energy, the energy of this radiation did not flow continuously as what we are predicting, but it flows as packet. That's his prediction. That's Mr. Max Planck gave his Planck constant hypothesis. It states that the energy of that radiation was directly proportional to the frequency of that radiation. And we remove the proportional, which use the constant here, this which is H is E all over F. And that constant was what we now refer to as his Planck's constant Js. That is the Planck's constant. That is what is on the board for you there. So that was his prediction. And I've just summarized there. The energy does not flow in continuous increase, as you see the diagram. It flows in step. That is a packet of energy, and each one has a relationship with its frequency. That was an assumption that needed to be done so that we can explain why this deviation took place here. So I am going to summarize the lesson here as I give you this question as an assignment. What discrepancies between experiments that helped lead Max Planck to a quantum theory? Remember what I said about the discrepancies, that the classical physics did not match with what they observed on the data. So somebody needed to bring another theorem that will explain what they have seen. And Max just guessed. He said that the energy did not flow in continuous flow because of nature of light, but now he found out that let's assume that the energy is now flowing in terms of quanta or packet or steps or energy levels. And when he assumed that, this just worked. So it was like a breakthrough. So Max Planck was the one that theorized there and gave us that relationship, and that one works. So you can now, from what I've said, be able to answer the question. What discrepancies there? The options are A, discovery of the cathode ray, B, the discovery of X-ray, C, the electroviolet explosion. And that tells you that this did not reach the UV. This is ultraviolet zone. That was a big error there that did not reach here. That's an explosion. So you must have got the answer from that. So we'll stop here for this lesson and we'll continue when we come back. Watch out for the next lesson.